Up to now, we have derived the diode equation that describes the current-voltage relationship of the p-n junction. Before we move on, let's spend some time to understand the behavior of a p-n junction and the meaning of the equation. p-n junctions have asymmetric conduction properties with very large forward current and very small reverse current. To understand why it is the case, let's use the water analogy again. Imagine that the band gap sort of represents a piece of landmass like a beach. On one side, there are a lot of electrons because the Fermi level is closer to the conduction band. And in the beach analogy, the water table is closer to the surface of the landmass. These electrons are like water vapor molecules from the ocean. From now on, I may use electrons or water molecules interchangeably when describing this picture. When reverse bias is applied, it is like the altitude of the beach rise, and the water on the beach is driven back to the ocean. As there is very little water on the beach to begin with, this water flow, which represents the reverse current in a p-n junction, is very small, like dripping. For forward bias, the ocean floor is raised, and the water molecules flood to the beach, causing a large amount of water flow like a tsunami. This is what happens in a p-n junction. If we examine the diode equation, it has an exponential term indicating the diode current increases exponentially with the applied voltage. The exponential term comes from the Fermi-Dirac distribution function after the Boltzmann approximation. It indicates that the number of carriers having enough energy to surmount the barrier to enter the other side of the junction increases exponentially with applied voltage.